y-axis, that's my y-intercept from here. And then to get to another point, I go down 1, over 1. And so I have a line like this, right? That would be the equation of that line. We're not at, but that's not what we want. We want to know what ordered pairs, right? What x and y's make this true. So the first thing we do is we draw the line. And now what we do is we determine whether or not our solutions are above this line or below this line. We have to figure out, like this line kind of creates two regions. And the way that I always tell my students do this is to do that, to check it, just pick a point and test it. Test this point. What happens when you plug 0 in here? Into here, into this. Is it true or false? It's true, right? If I plug 0 into there, I get 0, that's the y-coordinate, is greater than or equal to -1. That's true. And since that's true and this point was above, that means everything up here, everything up there is valid. Okay? Now, do we include the line or not? Yes, because it had a bar here, right? If this bar wasn't here, I would have to do a dotted line and not include the boundary of the line. Okay, so far, right? So far, my answer is this. So far, this picture. But is there any other domain restrictions? There's a problem here as well, right? What does this tell you? X cannot be what? 3. What does that look like over here? What does x equals 3 look like here? X is the left and right, right? So it's x is 3. How do we do this? X is 3. Let's say 1, 2, 3. What is it? Do I just take out this point right there? No, you have to take out the whole line. So how do I do that? I just put a dotted line through here and just realize that those points are omitted. So if I'm trying to graph this domain, here's what my final answer would probably look like. It would be like, here's my line, right? And then I have that dotted line here. And so it's pretty much like everything in here and everything there, right? I just have a lot of stuff written here, so I'm just trying to get you to see like that's what it looks like, right? So it wanted us to determine the domain and then sketch it in R2. Here's the sketch of the domain. To actually write down what the domain is, I'm going to write it the way it would need to be written technically. So I'm going to erase this. So I put something like this. The domain of F, right, is the set of ordered pairs, right? Remember, our domain are all the ordered pairs that live on the ground here, okay? So I put the domain as all ordered pairs, and you can use a comma here, or you can, not a comma, sorry. You can use a bar, or sometimes books use colons, but usually I use a bar. This bar, anyone know what that stands for? Such that, okay? So the domain of our function is all the ordered pairs such that, first of all, x plus y plus 1 must be greater than or equal to 0, and x cannot be equal to 3. That's the way we would write that domain. We're saying as long as you satisfy that inequality, and as long as x isn't 3, you're in business. That's the visualization of that domain. Now, determine the range. This is harder to do. The range is a much harder question. Like, the range is the output, right? Do y'all think, because we plugged in 2 numbers, didn't we? Or 2 ordered pairs. We plugged in 2, 1, and we got -2. We plugged in 0, 0, and we got a negative. Do you think we could ever get a positive out of this? Do you think this function ever spits out positive numbers? Yeah, we could figure out some, right? How about if x is 5 and y is 1? I'm just throwing some things out here. 5 here would make that positive. 5 and 1, I can make that positive. So there's going to be positives, right? Just depends. So I'm getting negatives and positives out of this. But as far as like how high up and down, it's hard to say. Maybe we need to look at it, right? Maybe we need to look at the visualization of this. Like the actual graph of the function. So how do we graph it? Well, we need to first understand that the whole idea here is that when I start plugging in points, right? When I start taking points and start plugging them in, for every point I plug in, for every x, y, there's either a point, or if it's outside the domain, we don't have anything, right? But imagine all these points together, right? What would they make if you put all the points together? I mean, eventually, right, if you do enough of them, right, you start to get what? What is this? Surface, right? If you do enough points, I have to have more points in there. Okay, so if you do enough points, you start to create a surface, right? So a function of two variables is going to graph, when you sketch the graph in three-dimensional space, is going to be a surface. That is much different than Cal 1, right? Cal 1, right? Y is some function of x. We have that on a flat sheet of paper. Now what we're doing is we're saying z is a function of two variables, and what does that look like? Well, that's three-dimensional, and it's some surface, right? That's a terrible surface, but you get the idea, right? It's some I think of it like a blanket, like if you like wave a blanket and just like freeze it in time, like that blanket is your surface. And so what were the questions that we asked in calculus here? Like what was the main fundamental idea here in calculus? Yeah, go to a point and find me the slope of the tangent line, or the tangent line, right? What do you think I could ask here? Go to a point and find the slope of the, yeah, but how do you define tangent, right? It seems kind of weird. Like, think about this surface right here. If I were to go to a point, right? If I were just to go to some random point, let me just pick one, right? I don't know, right here on that little ridge right there. Not on the top, just right there. If I pick that point, do y'all see that the tangent line doesn't make a whole lot of sense because I could be pointed in different directions? Like I like to think of it if I were standing here on this was like a hill, that'd be a pretty badass little terrain to be on, right? A little dangerous, but imagine I'm standing there, right? If I'm standing there, right? Here's me standing here. Right? If I'm standing there, then if I look this way, right? Then when I take a step in that direction, I'm probably going to go up, right? At a certain rate. But if I face maybe this direction instead, I'm going to be going down, right? And if I turn a little bit more, I might be going down a little faster or a little slower. Yes?
So is the tangent a plane?
A plane. A plane would make more sense, right? A tangent plane, not a tangent line. And so that's what we'll go get. We're going to go figure out the tangent line, or sorry, the tangent plane on a surface, okay? And what do we need for a tangent plane? What do we need for a plane? Normal vector and a point, right? So seems reasonable that we should be able to find a vector and a point there. What else do we do in calculus? Looking at functions back here. What I'm trying to do is like show you where we're kind of heading, all right? In Cal 1, we had this curve, tangent line. We're going to do that, tangent plane. All right, and then we get to Cal 2 and we say, go from A to B and get the area underneath that. What would that be here? Volume underneath the surface, right? Can we figure out, if you have a surface, what the volume below it will be? Now, don't confuse that with Cal 2 when we were doing this, the solids of revolution. When you would have a curve or intersection, you would wrap them around axes. Don't confuse that with this. This is a surface, and we could talk about the volume below it, right? That's going to be a big thing in this class, trying to be able to do that. All right, so let me back this out of here because it's slowing my computer down a little bit. All right, so the takeaway there is that we have surfaces, right? And this is the same picture. This just shows you again that for every point right? For every point down here on the ground, for every point down here, there's some point up on the surface, right? All right, here is the graph of the function. Oh, shit. Man, damn it, I kind of blew it already. Let me reevaluate this notebook. Why is it coming in like that? That's not what I wanted. That sucks. There, that's what it was supposed to do. Let me get this guy out of here. All right, do y'all see that that's the domain that we just did for that problem? Right, it's like this line, and then don't have anything at x equals 3. And what I'm showing you right there is an actual graph of this surface if you were to be looking from the top straight down, right? You don't see that? But let's let the computer actually help us see what it looks like. And if I twist this out here, you can see here what the graph looks like. And what's happening there at that line is an asymptote. You have a surface that the computer's having a really hard time because what you're getting along that line is like a vertical asymptote back in college algebra when you had this going on. We're having that happen, but with our surface. So the computer's kind of giving up. But it's kind of cool to see it. See the computer try. Let's see GeoGebra try that one. I haven't done that here. Delete, delete, delete. Okay, it was square root x plus y plus 1, I believe. And then divided by x minus 3. So there's GeoGebra's attempt at it. Whoa. I'm trying to get it to do something else. All right. I liked mine better. But you get the idea, right? All right, so there's that one. Let's look at another example. Can everyone see that function? Do I need to make it bigger? Yes.
So that bedsheet function.
Yes.
That wasn't derived from the equation that you.
No. That was just like generic.
Oh, okay.
Yeah. That bedsheet was just so we remember that when we have z equals a function of x and y, what we should see is a bunch of points, right? Whichever points are in the domain, we'll plug in, and what we see should be something like a sheet floating in the air. Yes.
Did we ever actually finish determining the range of that previous function?
No, not algebraically, and we won't do it algebraically. Visually, could you tell?
Yeah.
What would it be? It looked like, it went drop down, right? And it went up, so it looks like everything between negative infinity and infinity. That's what it looks like. I put here determine range, but that's really more of just like an exercise in us looking at the graph of it. All right, what about this one? F of 2, 3. Or sorry, 3, 2. Does the order matter? Absolutely. Sorry, I said that wrong. F of 3, 2 means we have 3 natural log of 2 squared minus 3. Yeah, right? That's right? Okay. So isn't that 0? Yeah, that's 0. Natural log of 1 is 0. So when you plug in 3, 2, right? When you plug in 3, 2, you get 0. That would be considered a what intercept? Not an x-intercept. It would be it's kind of, how do you say that, right? Yeah, it's just, that's where you intersect the xy plane. Somewhere at 3, 2, you intersect the xy plane, but you can't really call it an x-intercept, right? All right, how about the domain? So look at that function up there and tell me about the domain of that. What about logs? What is about logs? Inside of a log, you got to have what? Positive only. So we need, right, for the domain of f, we need the argument of that log function to be strictly greater than 0, right? Strictly greater. The y squared minus x has to be greater than 0 for this thing to be defined. Now this is not a linear inequality. This is a quadratic inequality, and these you have to be careful with. Again, how do we solve these? I'm going to turn it into an equation. I'm going to write that down. I'm going to graph this function. Or sorry, graph this equation. Do you all know what x equals y squared looks like? It's a parabola, but it opens which way? Sideways, right? So it goes like this. Like that. That's what it does. That's the equation, right? That's this. What we want to know is when this is true, right? So do we want to include the actual parabola itself? No, because there's not a bar here, we don't want this to ever be actually equal to 0. So I take out that. And now I need to check a point. And that point either needs to be kind of like to the left of this parabola or kind of like inside the parabola. I cannot pick the origin, right? Because the origin, the graph goes through there. So I'll pick some other point. How about I pick 1, 0? Does 1, 0 work? 1, 0 works. You have to be careful with the order of things here. Let's see. 1, 0 goes here. 1 goes here. I don't think it works, does it? No. If we take that and we plug that in here, we get 0 squared minus 1 greater than 0? Question? No, it's not, right? So that doesn't work, right? Which means our domain is this stuff on the outside of this parabola, like this. Now remember, it keeps going, right? This parabola keeps widening out. And we're just, as long as we're outside that parabola, then that's in the domain. All right, y'all ready to see this one? You ready to see it? God, I keep giving it away. That's so lame. There we go. That's it. That's looking at it from the top. That's the surface looking at it from the top. And y'all can see this domain, right? Can see that domain?
The top of the shell and everything else around it.
Yeah. Now let's actually rotate it so we can see it. That's what it looks like. Now, see how it's all jagged and stuff on these edges? That's just the computer kind of giving up, right? And the computer's just kind of like, okay, I don't know what to do. I'm going to negative infinity, and just kind of waves its hands at it. Like it doesn't actually end like that. Okay. What about this one? Let's just talk about domain of this one. The 9 minus x squared minus y squared, that's x squared minus x squared. X squared minus y squared, that must be greater than or equal to 0, right? For us to be able to do square root? Okay. Well, that kind of looks like this. 9 must be greater than or equal to x squared plus y squared. If I bring the x squared and y squared to the other side. Does that look familiar? Like if that was an equal sign, this would be a what? If it was equal. It would be a circle of radius 3, right? But if we want this to be smaller than or equal to this, what do you think it is? It's not a circle, it's what? So I'll do it the way I said. Turn it into an equals first, right? And you said that's going to be a circle of radius 3. Now test a point. Let's test the origin. Does the origin work in here? Yeah, so that means everything in here works. And that means this is actually the inequality that represents the disk, right? The disk including the boundary of radius 3. And that should be our domain. That should be the domain of this. Let me try this one. Okay, there it is from the top, right? There it is from the top. And you ready to see it? There it is. Does it make sense to you that that's what it is? What was the original function? F of xy equals 9, square root of 9 minus x squared minus y squared? Okay, but didn't we say that the f of xy really means z, doesn't it? So z is this, right? Square both sides. What happens if you square both sides? Z squared, get rid of the root on the right, you get 9 minus x squared minus y squared. Take all your variables over to one side, and you get x squared plus y squared plus z squared equals 9. And that's the equation of a sphere centered at the origin radius 3, right? So, right? Now, why don't we have the whole sphere here? Because, well, it wouldn't be a function, would it? Right? Like it wouldn't be a function if we were to say plug in a number and now you have two outputs, the top point on the sphere and the bottom, which is why when it's solved for z here, you have to take, right? If I told you to solve this for z, right? You go backwards here, what would you have to do this step right here, from here to here? What am I missing? Plus or minus, right? So we're only looking at the positive case, which is why we're getting the top of it. If we looked at the minus, it would give us the bottom, right? So do not think that this is the equation, or this is a sphere. This is only the top half of the sphere. All right, now we extend the idea. There's nothing that says that we can't have a function that takes in 3 variables, right? Instead of me giving you x and y and plugging that into some function and getting z, what if I give you x, y, and z, plug that into a function and get, where is it? See, I'm plugging in x, y, and z into a function and getting some answer, and where do I put it? Where do I put that answer? In some other dimension that's not here, right? So it's going to be, we won't be able to see this, right? We won't be able to see this. But the idea is still the same, isn't it? The concept is still the same. We can have 3 inputs in 1 output. In that case, we would have a function that would be f of x, y, z. That means, again, we're taking our domain, our points in 3-dimensional space. The range is a number, and so we need 4 dimensions to visualize that, and that's not going to happen. But we can still talk about the domain. We can still at least try and discuss the domain. So look at that one right there. It's very similar to the problem we just did, except I've got 3 variables in there. You'll see that? See the notation? F of x, y, z. F of x, y, z. Give me 3 inputs, the x, the y, and the z coordinate, and then I will give you some number. Let's find f of 1, 2, 0. What would that be? 9 minus 1 minus 4. Wait a minute, minus 0, is that right? Square root of 4? 2?
No, 4? That is 4.
Yeah, 4, right? 2? So just 2? So let's see if y'all can, maybe y'all can think about a function that would actually be useful. Like this would be a useful thing. We're saying if we plug in 1, 2, 0, that means if I go out 1, go over 1, 2, and then don't go up or down. So go out 1, go over 2. Right here, that point, I'm going to plug that point into a function. It's going to spit out the answer 2. Right? Maybe that's the temperature at that point. Right? Maybe it's the temperature of that at that point in 3-dimensional space. Maybe that 2 represents, like I said, it could be temperature. It could be, maybe that 2 represents the gravitational acceleration constant at that point. And as I move around, it changes perhaps. Or if I move around different places, I have different temperatures, right? So it does make sense that you would have an input that is a position, and then the output is some physical quality of what's happening, some measurement of what's happening at that point, right? It doesn't have to be, but it could be. Okay? All right, what about the domain of this one? Well, you have a square root, right? So what do you need on this function for it to be defined? we need 9 minus x squared minus y squared minus z squared to be greater than or equal to 0. But if we change that to an equals, what do we get? So 9 equals x squared plus y squared plus z squared. This is a what? Sphere. Right? Radius what? 3. And we need to check. We need to check, is it the stuff inside the sphere or outside the sphere? Because remember, it's an inequality here, right? Here it's an inequality. Here we're doing an equals just to draw it. So let's check a point. Let's check 0, 0, 0. Does that work or not? Does 0, 0, 0 work in that? It does, right? It works, which means we want everything inside this too. So it's actually the ball, the solid ball of radius 3 is the domain of this function. So it's this solid ball, radius of 3. That's the domain of that function. We could visualize a domain, right? It's like you have a ball here of radius 3. As long as you are talking about the ball of radius 3, any point on it or in it or, then this function is defined. You go outside that ball, this function doesn't make sense anymore.
So because it's the input and not the output, it's okay that technically that ball doesn't pass the vertical line test, right? So like, since
That's right.
Okay.
Yes.
Domain. Okay.
Yeah, because your output is in some other dimension.
Yeah.
So you don't have the idea of that vertical line test. Yep. Yep, good point. All right. So the homework for this section is problems 1 through 12. It's very much like what we've done here. And I say try the range. Go to GeoGebra, type it in, see if you can tell what the range is from the picture. Now, you won't be able to type in functions of 3 variables. Right, just 2. So before we get into the next section, I just want to kind of recap again. This is everything you've done, right? Everything you've done leading up to today has been a function of a single variable. There we took a real number in, and it spit out a real number, right? Real number in, x went in, y went out. So how do we visualize a real number going in? We use a number line for the input. How do we visualize the output? A number line. What's the best way to visualize this together? Is put the 2 number lines perpendicular to one another, input, output, and then you get the graph, right? You get the graph of the function. So this is your in, this is your out, right? In, out. Now, what I'm saying is we can have a function z is a function of 2 variables. That goes from 2-dimensional space into 1-dimensional space. How do we visualize 2-dimensional space? A flat, xy axis, right? This is our input. And our output is a number on a number line. This is our out. What's the best way to visualize those together? Draw them like this. Where your ground is your input, right? This is your x, your y. That's your input on the ground. And then your output is your z. That's your out, right? Those 3 axes together, right? Okay, and then what we just did, we said, okay, if you have some function of 3 variables now I didn't say what to call it, right? I didn't say it's equal. We can't say it's z, right? Because we're already using z here. I don't know, I'll make it up. How about t, capital T? I'm just going to make that up. So that means for your input, right, this goes from R where to where? R3 into R, right? And so to visualize the input, you need 3-dimensional space. And then you need another dimension here for the output, and then that's a sad face, I guess. Terrible, whatever. Not going to happen, right? Cannot visualize that 4-dimensional space. Right, this was 3-dimensional space. This was 2-dimensional space. This is 4-dimensional space, which you can't visualize. And there is absolutely no restriction when it comes to functions in math in terms of dimensions. You can have a function that goes from any dimensional space into any dimensional space. It does not matter. Okay, we can have it. You can have something that takes in 4 inputs and spits out 10 inputs. or has 5 inputs and spits out 2 outputs, right? Do you want an example? I'll give you an example. I'm going to define a function. F of x, y, z, r, t, and it's going to be, my answer is going to be x plus t squared minus r, y squared minus the natural log z, and then how about r raised to the t minus z raised to the x. Okay, there we go. I've just defined a function there. This function I defined goes from where to where? What dimension to what dimension? R5 to R3. I'm taking 5 inputs and giving you 3 outputs. Now, this doesn't make any freaking sense. I'm just making it up. I'm just trying to get you to see that what we do here is still very limited because we are staying in spaces we can see or at least 1 dimension over, like 4th dimension. But generally speaking, we need to be able to do calculus in any dimensional space, which we do have the calculus for it. Okay, it's there, we have it. But we are going to stay still in Cal 3, just kind of at the edge of it, right? When we look at something like this, think about like a computer, right? I think I talked about this in the past, where maybe X, Y, Z, R, and T are like temperature, humidity, pressure, relative, I don't know, whatever, 2 other variables, right? Wind speed, solar energy, I don't know. You've got 5 inputs, right? And then somehow the computer takes that and it spits out like probability of rain, right? This is like probability of strong winds, but like you have 3 outputs, right? 5 inputs, 3. But in the real world, it's probably more like 30 inputs and like 3 or 4 outputs. Yes.
So this is kind of a weird example, but does this count as like a representation of like a 4th dimensional, like something in R4, which is like when you watch like the news and they're showing the weather and they have like let's say like a map of Texas and there's like a hurricane or something coming in, like it'll show like they use different like colors for like the intensity of it, like so you have like the X and Y to show like where on Texas there is, and then they have like colors to represent intensity, and they have like a little animation of like how that will like change over time. So that's like 4 different things, right?
Yeah. Well, you have X and Y, right? X and Y give you position. And then you have the color would be your 3rd?
Yeah.
Okay.
The intensity of like
the intensity, yes. Yes. Which you, because now that's because they're on TV and it's flat, right? Yeah. But in a 3-dimensional model, you've seen them, right? Nowadays they can like turn the models and you can see the storm like in 3 dimensions. I mean, you could have there a 4th dimension where you have the clouds and the clouds have different colors within the clouds, but it's hard to imagine, how do you see through a color to the next color behind it in 3 dimensional